I'm very good. Thank you for having me.
You're very welcome. Just so people, briefly through your CV, just last year you won the Young Scientist Award in General Relativity and Gravitation from the International Society on General Relativity and Gravitation. In 2010, you won the Einstein Fellowship from NASA, and the list goes on and on and on. You've devoted your life's work to Einstein's theory of general relativity and gravitation. How's it going?
It's going great. Now, it's very exciting times because lots of discoveries are being made right now. It's really a great time to be alive and be working in gravity. You know, gravity was discovered, general relativity was discovered in 1915. In fact, it's been a century now since Einstein presented his results and, published them. In fact, he published them in March. So in March, it'll be 100 years. Mm-hmm. And it's taken us that long to verify and confirm all of the predictions that Einstein had made. Of course, back then they didn't have the technology to go and place a satellite in orbit and say, oh yeah, clocks actually tick at a different rate up there versus on Earth. Today, we have clocks that are so accurate, these atomic clocks, mm-hmm. that if I place one on my head, like by my head, and another one by my waist, I can measure that they're ticking at different rates. That's how accurate technology has become, and that's one of Einstein's predictions, that clocks tick at different rates depending on how strong gravity is. And as we were talking about earlier, gravity, by my head is actually weaker than gravity by my waist because my waist is closer to the center of the Earth than my head is.
So that's why my feet hurt all the time.
That's right.
The reason why I invited you here, and hopefully this will develop into an ongoing series, a conversation with Eric Loberg, the director of the Taylor Planetarium, the idea of gravity came up, and I started thinking about it afterwards. Okay, I can understand the effects of gravity. As many of my listeners pointed out, you throw a ball into the air, it drops to the earth. That's the effect of gravity. But what is gravity? Is it a wave? Is it a particle? Is it some mysterious mojo of the universe? What is gravity?
Gravity is what makes things go round. That's how I like to think about it. Gravity is a force, mm-hmm. Okay? What is a force? A force is something that induces motion, okay? So if I push you, if I exert a force on you, then in reaction to the force I just exerted on you, you will move backwards and maybe fall, mm-hmm. Okay? So gravity is a force that makes you move toward other objects that are producing that gravity. Okay, so right now, you and me produce gravity, if you want, because we have matter, and matter produces gravity. And the effect of that gravity, and since I said gravity is a force, the effect of that force is to want to make you move toward me and to make me move toward you. We attract each other. And the same happens with Earth and anything that lives on Earth or around the Earth. Earth is very, very massive. So the gravity that Earth generates dominates over pretty much anything near Earth or on Earth. Okay? So anything that's on Earth feels attracted to the Earth. So gravity, or the force of gravity due to Earth, makes you not fly away into the cosmos and, not be attached to the surface of the Earth.
I forget what axiom or theory it is, but nothing is neither created nor destroyed. It's just energy. It changes. Is gravity, even though it is a force, is it an energy?
So, in order to understand that, we have to... the way I was describing gravity has more to do with a Newtonian point of view of gravity from the 1700s mm-hmm. or so on. But in the 1900s, things changed. And a guy came, a German scientist, I think he was Jewish, Albert was his name, and he said that energy and matter are sort of interchangeable. That you can convert energy into matter and matter into energy, the famous E=mc² equation. Okay? In fact, that was part of the special theory of relativity. Not his crowning achievement, that would be the general theory of relativity, but still an astonishing discovery in 1905. Which, by the way, was related to the discovery of the photoelectric effect, which today gives us solar cells, which is the thing that got him the Nobel Prize later on, and so on. if you think about gravity from Einstein's point of view, he said, well, I don't like this idea of forces because, according to Newton, this force of gravity should have been instantaneous. As soon as I enter the room, you instantaneously feel my presence. And instantaneously you feel attracted toward me because of the gravity I generate. And Einstein didn't like that. He called that spooky action at a distance. Spooky because nothing should propagate instantaneously like that. If that were the case, you could imagine paradoxes where you could send signals back in time essentially faster than the speed of light. And that breaks causality and all sorts of problems arise. And we really don't want to run into those logical paradoxes. So he said, there must be another explanation for gravity. And he said, well, what if gravity were just a manifestation of the curvature of space and time? So he had already discovered that time was not absolute when he constructed a theory of special relativity. And neither was space, in fact. What he discovered is that objects that are moving very, very fast, their internal clocks tick at a different rate than clocks that are not moving on Earth. So since time and space are not absolute, perhaps they're also not absolute due to gravity. And he worked out the mathematics and discovered that indeed that was the case. Gravity was the curvature of space and time. And so from that point of view, matter, which is a form of energy, creates gravity. Okay? And that curvature of the geometry is what's sourcing or creating this force, if you want.
Yeah, I mean, I guess the classic example is if you put a bowling ball in the middle of a trampoline and then roll a bunch of marbles onto the trampoline, you see how they circle the bowling ball in the center.
Right. Or even easier, just put the bowling ball on the trampoline and then just drop a ping pong ball from the edge, and the ping pong ball will just roll toward the bowling ball. Now, imagine that you didn't see the trampoline there. And you were just doing an experiment, and you were observing the ping pong ball move toward the giant bowling ball. You could imagine that there's a force between the bowling ball and the ping pong ball that's attracting the ping pong ball toward the bowling ball. But that's because you're not seeing the fabric of the trampoline.
And that's what we refer to as space-time?
Yes, that's right.
So are gravity and time inextricably linked?
In some sense, they are. If you think of gravity as the curvature of space and time, there's not a way to disentangle space, time, and gravity. And that's why Einstein's theory is so complicated.
But why? Well, I guess, because I guess the Holy Grail now is the unified theory, to take everything from the macro to the micro. And where does the challenge of gravity play in that, in the role of the unified theory?
Well, so there's two theories that we cannot make, we cannot unify, we cannot make them play well with each other. If you want. One is the quantum theory of the early 1900s, which Einstein helped develop, and the other one is the gravitational theory of the 1900s that Einstein developed. So he sort of contradicted himself in some sense. These two theories are mathematically incompatible. We cannot unify them for very technical mathematical reasons. Which means that the idea is that the suspicion is that one of these two theories must be wrong in regimes where gravity is very, very important and you're probing very, very small length scales. So, for example, one of the consequences of Einstein's theory of general relativity is the existence of black holes. Everybody loves black holes. These are the incredibly dense, completely gravitationally collapsed stars. Not even light can escape these objects. And so if you fall into a black hole, apart from dying, what you would experience as you get close to the center is you would begin to sense or feel the singularity. If you want, the singularity is a point at the center of the black hole that in Einstein's theory of gravity has infinite pressure and infinite density and infinite energy, and that's impossible because nothing has infinite energy, infinite density, and infinite pressure. So there has to be something perhaps not quite right with Einstein's theory, right at the singularity, right when you are probing length scales that are 10 to the minus 30 meters in size. And that's precisely the regime where quantum theory should be important. Mm-hmm. So one suspects that in order to fully understand or resolve the singularity problem, one really needs to come up with a theory that unifies Einstein's theory and quantum theory. And that's perhaps one of the holy grails of physics. And there's lots of people that have been working on this for over 60 years, and progress has been very slow, but very exciting as well.
Well, because I know that one of your specialties is black holes. Oh, by the way, it's 1450 KMMS, 1340 KPRK, MSU physicist Nico Yunes in the studio. One of your specialties is the dynamics of black holes, and you say everything is attracted to a black hole, yet there was just black holes discovered that are expelling matter. But it's, they found two coexisting black holes. They think one is sucking matter out of one black hole into another.
Interesting. I have not actually read that story.
Oh,
was that a movie you watched?
No. I think I still have the email somewhere in my folder here. We can get it.
I can sort of imagine what could happen. Mm-hmm. So anything that's inside of the surface of a black hole cannot escape the black hole, according to Einstein's theories. That's sort of impossible. But that doesn't mean that things that are outside, right outside of the black hole, can't escape. Things that are right outside of the black hole, or any distance outside of the black hole, outside of the surface of the black hole, can escape. Mm-hmm. So it turns out that black holes are excellent at collecting garbage in the form of gas. They're hoarders. They're the ultimate hoarders of nature. Okay, they collect gas, they collect dust, all sorts of material that's near them, and this material collects itself into disks, just because that's the most stable and energetically favorable configuration. So these disks slowly, they are made out of this dust and gas, and this dust and gas slowly falls into the black hole. So we say that the dust and the gas and the material in the disk accretes into the black hole. That's why we call these disks accretion disks. Okay?
Yes.
So if you have a black hole with an accretion disk, and then there's another black hole nearby, it is, in principle, possible that some of the material on the farther edges of the accretion disk would begin to fall into the secondary black hole. In fact, there are circumstances where like two black holes with accretion disks collide against each other, or sort of begin to spiral into each other. But before the black holes touch, if you want, the accretion disks touch, and they begin to interact. And then very complicated and fascinating dynamics happen because, of course, these accretion disks have to, they collide with each other and they interact, and all sorts of radiation can be produced until eventually a single circumbinary disk is formed around these two black holes that are moving around each other. And we, in fact, expect those to be excellent sources of radiation that we might be able to observe, for example, when galaxies collide.
It appears to me, and please correct me if I'm wrong, it's easier to study gravity on an interstellar scale than it is on Earth.
Well, the problem with studying gravity on Earth is that we can make very, very precise measurements. Mm-hmm. And that means that we have to control our sources of noise very carefully. So when we study gravity on Earth, we have to worry about the fact that, for example, an airplane might be going right over our lab at random points in time that you have no control over. Or you might have to worry about the fact that maybe 100 miles away from your instrument, they are cutting down trees. And those trees fall to the ground, typically, not gently. They fall violently to the ground. And then guess what? They make the ground vibrate. And on top of that, turns out Earth shakes and quakes all the time. And we don't feel it because the vibrations are too weak. We only feel it when the vibrations are large. We call that an earthquake. Or if it happens in the ocean, a tsunami, whatever. But it turns out that it's vibrating all the time. And our instruments are sensitive enough on Earth to see all those vibrations. And we can't, shield our instrument from gravity. That doesn't make sense. There's nothing that can shield you from gravity or from vibrations on Earth. So the only way to really get a pure, clean measurement of gravity is to get away from all the sources of noise And our best... Oops.
No, that's all right.
That's my cell phone, which I forgot to turn off. My bad.
No worries. It's happened to everybody.
It's off now. So that's why it's good to leave Earth, so that we can isolate ourselves from sources of noise. So, for example, right now, one of the exciting reasons why studying gravity is quite timely is that we are about to discover gravitational waves. We were talking about that in a break earlier on. What are gravitational waves? Perhaps that's a topic for another day. But needless to say, they're very important, and it's the last thing that Einstein predicted effectively that has not been seen yet, has not been directly confirmed. And there's 5 massive collaborations around the world trying to measure gravitational waves. And it's so difficult to do so precisely because of all these man-made or women-made sources of noise. In spite of all those sources of noise, the experimentalists and instrumentalists are so good that they have managed to make precise enough measurements to hopefully have detected gravitational waves. I mean, it's not... Everything seems to indicate that the waves will be detected within the next few months because the instrument is running, and the longer it runs, the more accurate, the higher the sensitivity that we have to these waves. So we should be detecting them anytime now. And I know there's rumors that they have already been detected, but there's nothing official from the collaboration. It's just rumors.
So, because we started and you explained to me that gravity was a force, and now it may be a wave?
It's a wave! No, so gravity is always a force. It's just that there's something else called a gravitational wave that... some other day I'll explain to you in more detail because that's an entire rabbit hole to go into. But regardless, you can detect these gravitational waves, which is a consequence of Einstein's theory. It doesn't, they don't exist in Newton's theory, okay? So it's yet another confirmation of Einstein's theory. And this is going back to your initial question, there's a very serious effort by the European Space Agency and also by NASA now to take these instruments that have been built on Earth to detect gravitational waves and put them up in space, to put them up in satellites. Why? Because nobody's cutting trees down in space. Nobody's flying a plane yet through like the moon or around the moon. So if you place these satellites sufficiently far from Earth, sort of behind Earth in an orbit, just like Earth goes around the sun, the satellites would also go around the sun, then you could essentially place the instruments that are on Earth in space and get rid of all of this noise. And that's why, sometimes making measurements in space is so much better than making measurements on Earth.
Joining me in studio, MSU physicist Nico Yunes. We have just a few moments left. Actually, we're already over time. Nico, why is physics important?
Why is physics important?
Yes, I mean...
Excellent question. So, look, because of the work that physicists have done effectively today, and the effort to send people to the moon and so on, we have, electricity, television, radio. The miniaturization of electronics that then led to the computer revolution was prompted by NASA. It was so that they could send or put more computers into their rockets, and they had to be light enough and small enough so they could fit in the rocket because fuel is very expensive. And that is perhaps the biggest consequence of the space revolution of the 60s and 70s, not the discovery of Velcro, like most people think of,
Right.
And today, people might be arguing, well, that's in the 60s and the 70s. What has science done for us, or physics in particular, since then? Well, there's a set of computers that got connected to each other in Switzerland and in the United States in the in the 80s and 90s that then allowed scientists to communicate with each other. And they thought, this is a great idea. Communicating through a computer. Wow! And thus the internet was born.
Right.
So the discoveries that you make in basic research unavoidably then trickle down into economic development and pushes in technology and in innovation. You cannot have economic growth without innovation, in my mind, even though I'm not an economist. What I do know for sure is that you cannot have innovation without pure basic research.
So I can blame physicists for Facebook.
Yes, you're welcome. I want my cat also. Maybe we should contact Mark Zuckerberg.
Well, Nico Yunes, I thoroughly enjoyed the conversation, and I hope you'll come back. I think we're going to work out the details a little later this afternoon, whether you're going to be back on a weekly basis or a bi-weekly basis. I appreciate your time, and good to see you again.
Thank you very much. Thank you for having me.